Okay, well, I hope everyone can hear me all right. So let's get this seminar going. My name is Hannah Radabaugh, and I am a graduate student working with Drs. Helen Bramlett and Dr. Dalton Dietrich. And today I'm going to focus this talk on a couple of ways that we can integrate machine learning into the world of traumatic brain injury research. So, with that, it's no secret that we as researchers and clinicians have had quite a bit of difficulty in identifying pharmacotherapies that effectively treat TBI patients. So, throughout this talk, I hope to address some of the limitations that have led to these difficulties, as well as the role that we see machine learning in addressing some of these limitations. So, briefly, machine learning is a subset of artificial intelligence that enables a computer to learn from and improve its performance with experience. Now, that experience is typically more data. So, performance is typically a measure of how accurately the machine can predict an attribute or event given a set of features. Now, these features will be whatever you have in your data set, something like blood pressure or score on a cognitive task, anything that you have in your particular study. So, this ability to make predictions is largely a combination of theories that we have from these particular mathematical fields. And now, this combination really leads to the power of machine learning in that it provides the tools necessary to analyze our data sets in a multivariate manner. That is, instead of the univariate metrics that we typically use, something like ANOVAs, that focus on one metric at a time, multivariate techniques analyze the dataset as a whole, thus highlighting the complex patterns that exist between data measures that are obviously missed when you look at one metric individually. So, in order to gain a more clear picture of what's going on, you can imagine your dataset as a matrix. Honestly, just think of your Excel spreadsheets. So you'll have a number of rows representing your subjects and then the columns with each of your variables. These data can then be plotted as a vector in a feature space of any dimension. Now that goes well beyond our 3D understanding, which then requires some sort of dimensionality reduction. Something like t-SNE that we've seen pop up a couple of times in our Miami project seminars can be used. And then if you look here on the right, each of those symbols, whether it's an X or a triangle, represents one sample in your data set. So one patient, one rat, whatever it may be. Keeping that in mind, let's take a look at the current state of TBI research. So modern research has detailed a number of the damaging mechanisms that underlie the deficits observed following a traumatic brain injury, such as inflammatory cascades or neurotransmitter imbalances. So theoretically, this should mean that we've identified therapeutic targets to treat these injuries. However, we all know that that is not the case and that the identification of effective therapies has remained elusive. So of course, we want to know what the heck is going on here. Why don't we have therapies? And we believe that one of the major issues that we as a field have failed to address is the fact that treatments that work in some cases fail in many others. So this is true in both the animal side of research and the clinical in TBI. And that range can actually be very severe in that one treatment might be beneficial for one patient and then actually completely detrimental in another. So while this is often attributed to the great deal of heterogeneity that we see in the clinical TBI population in terms of injury type, location, severity, various other injuries that occurred, it is urgent that we seek out ways to better understand these individual variabilities that are leading to the different outcomes. So machine learning actually provides the ability to highlight this variability between subjects in such a way that we may actually be able to identify specific subgroups and then a subsequent optimal treatment for those subgroups. And so far, the application of machine learning in the TBI field has actually been quite promising, but rather primitive in its scope. That is, major sweeping questions such as will the patient live or what variables are relevant in determining whether they will live have been tackled, but the more complex questions like degree of recovery or treatment predictions have yet to be widely explored. Furthermore, almost all of the work that has been done in the TBI field with machine learning has been using these large clinical data sets due to the fact that to make a useful intelligent system, you typically need a huge amount of quality data. So transforming these techniques into a form that is applicable to the laboratory is going to require a lot of insightful ways to generate and process these data. And those are some of the major hurdles specifically that my dissertation work is looking to address. So briefly, let's refresh our memory on what TBI research actually looks like in the laboratory. So we have a number of different injury models that mimic the different types of injury that you see in the clinical population, such as a more focal injury with a controlled cortical impact, or a more diffuse injury with a fluid percussion injury, and so on. So we do have many injury types represented, but for feasibility's sake, most studies or even most labs focus on one injury type. And this makes clinical translation difficult where the patient population is not likely divided to be or likely to be divided into the same groupings. So furthermore, in the lab, we attempt to frame clinically relevant deficits into quantifiable tasks in order to provide a way for us scientists to assess the effectiveness of the therapies that we're looking at. So on the bottom right, you can see pictured a very widely used task to assess learning and memory known as the Morse Water Maze. So I'm sure many of us are familiar with this task, but briefly, you're going to have a pool that's situated in a room with visual cues. A rat will then be placed into the pool and have to locate a hidden escape platform and remember where that platform is over time based on its location relative to those visual cues. Of course, this performance is severely impacted by a brain injury that we induced in the laboratory with the methods I discussed a moment ago, which then allows us as researchers to assess drug effectiveness on this aspect of cognition. Additionally, and take note because this will be very relevant in a second, we can also use this setup to do what's called a probe trial. Now, a probe trial measures memory retention because it'll take place many days or after the many trials and days where the rat has learned where the platform is, in which case we'll remove the platform and see how long the rat spends swimming in that target location, indicating that the rat did recall what it had learned on the days prior. These tasks then generate data sets that look a little bit like this, and the metrics will typically be analyzed one feature at a time using something like ANOVAs, looking for variance, or significance. Now, despite decades and decades of research, we failed to identify any kind of overly effective therapeutic strategy for these TBI patients. And as mentioned a moment ago, we believe this is due in part to the limitations of our current analyses, due to their inherent inability to capture the complexity of the TBI population. We therefore need to shift our current way of thinking when it comes to handling our data. But that's not exactly clear. And so what I hope to really address in this talk is whether or not machine learning might be the answer. So in an attempt to answer that question, we access the rich animal data set collected by the consortium study known as Operation Brain Trauma Therapy, or OBTT. So OBTT was a multi-center consortium that aimed at identifying a therapy for brain injury with a high likelihood of clinical success. In brief, they incorporated 3 different experimental models of TBI across these 3 particular centers, and then analyzed the listed metrics here. Although it was univariate, they employed a scoring system that would allow them to compare one therapy to the next, which is pictured here on the right. And now, what I want you to take away from this slide is that the top score in the scoring matrix was 66. As you may be able to see here, the best performing therapy got a 10. And I don't know about you all, but if I came home with a 10 out of 66 on my test, my mom was not putting that on the refrigerator. So, while these studies didn't necessarily uncover anything jaw-dropping, we did see a lot of potential in these data, given that the number of subjects, although still limited, is much greater than your typical animal data set. Additionally, these data are clean and tabular and complete, which is a checkpoint when you want to start applying these different computational techniques. So then, what the heck am I aiming to do personally? Forward this slide. All right. So roughly, these techniques have the ability to better inform preclinical research. As a brief example, imagine the infinite number of combinations of therapies that we could test for TBI. If we could establish a workflow that is effective in addressing the hurdles of limited animal data, then we could potentially use these techniques to help identify therapies with a high potential for additive effects. Clearly, this would save enormous amounts of time and resources that would otherwise be spent in brute force testing. So first, we have to have a better understanding of what these techniques actually look like in our field. So we're going to have to acknowledge and separate the types of data that we have in each of our individual data sets on the premise that certain machine learning techniques are better suited for different data types. That is something like an imaging, study versus something that's entirely quantitative or qualitative would be using different machine learning techniques. We then have to move into the pre-processing phase, where you're going to need a great deal of time and thought given to how we can teach the computer what we as scientists know. For example, you or I are trained to administer different behavioral tasks or tests within, the lab or the clinic, and we would be able to look at a data set very quickly and be like, oh, that's a bad score on whatever it may be, or that blood pressure is way too high. Whereas the computer wouldn't know that. It doesn't have the same context. It would just see a number and then compute that into the system. So keeping this in mind, we have to devise the best way to represent each feature relative to both itself, what we know, and the other features, because we can't have one scale completely outweighing another feature in the data set, or else you're putting on these arbitrary weights that don't necessarily mean anything in the context of our research goal. Moving forward, we then have to shape whatever research question we're trying to address as a machine learning task. And I'll go into a little bit more detail about that later. And then furthermore, we have to decide whether our research question requires the integration of multiple intelligence systems to build upon one another and give a final outcome. So briefly, exploratory data analyses is the important first step to training our machine learning model. Now, typically this consists of a number of techniques that we're all very familiar with that help us detect outliers, determine the distribution of our data, and identify redundancies present within our data set. Furthermore, machine learning techniques that describe some of the sources of variance, such as principal component analyses, which is a more common technique people may be familiar with, can be used to inform which features were relevant in the eventual prediction, or as a process feature vector for later model training. So briefly, we don't have to go through all of the details on this slide. It'll advance. Oh, my slide's not advancing. I'm not sure what, oh, there it goes, okay. So briefly, here's an exhaustive list of the, now it's gonna advance more than once. All right, well, I would have shown you an exhaustive list of the data pre-processing that occurred between the raw data set and the curated data set, but briefly, it was just looking at things where we would take differences between time points, say we had a 4-hour metric and a 24-hour metric. The actual relevant feature we wanted for our data set would have been the change over that time rather than two redundant measures. Furthermore, we had to consider things like scaling. So we normalized all of our features between 0 and 1, so we still had the same difference between numbers, but everything was on the same scale. And we also had to look at the features that were categorical. For example, treatment. We can't just assign 0, 1, 2, 3, 4, 5, because then 5 would have an arbitrary weight over 0 in a sense. So we have to use something called one-hot encoding, in which case we have a column for every single treatment and a series of zeros or ones to represent a categorical attribute in a quantitative system. So then what can machine learning teach us? So in an attempt to start hashing away at this question, we had to investigate whether or not machine learning could generate conclusions that conventional analyses may have missed. And you may remember this from last year's seminar. So in doing that, we asked the question, do conclusions differ between the traditional analyses and machine learning? So we framed the heck is going on? Reframe the question, can a machine identify treatment effects that were missed by the univariate statistics as an unsupervised clustering question? So in our case, this meant that the machine would be receiving no information regarding the treatment that each subject received, and we then asked it to provide the clusters based on the patterns and correlations that it discovered within the data set. So we then asked whether or not the machine was reliably able to determine which treatment each subject received. So here you can see one snippet of that OBTT data set I described a little bit ago. And I'm showing this one because it had a lack of significance across all metrics, a few of which I've showed here. No p is less than 0.05 or whatever your significance was set to. So, however, when we framed this as a clustering task, the machine was actually able to group patterns by the treatment that they received, whether it was that insignificant treatment, minocycline, versus the vehicle treatment. And this suggests that although it's far from perfect, and backs up all the heterogeneity in the data set, there are patterns and correlations within our data set that allow the machine to differ between treatment identity. And this suggests that minocycline actually did have some sort of effect on that multivariate functional recovery that we were testing. So knowing that these patterns exist, we moved forward with a degree of confidence that we could begin framing some more research questions as more complex machine learning tasks. Therefore, our next goal was to move into the world of supervised learning. So a prerequisite to any supervised learning task is to clearly define your input and your output. So as an input, we decided that the question we were going to explore was whether given metrics from the first week following injury, so that's our input, those first 7 days, could a machine predict how well each sample was recovering a full month later? So our input being the first 7 days post-injury in OBTT means it includes physiological data such as blood gases, temperature, blood pressure, and so on, biomarkers associated with neuronal and glial damage, and gross motor function. But defining an output class is a little bit trickier. And this requires us to identify a measure of functional recovery that is both clinically relevant and empirically well suited for our goal. So what this means is we need a metric that's relatively evenly distributed in its distribution so that we can create a binary class attribute. So if we're going for something that says recovered versus not recovered, you can imagine if we chose an attribute where 95% of samples belong to, say, the recovered bin. A machine could guess recovered every single time, reach 95% accuracy, and we might say, yeah, that's great, it's trained really well. But that doesn't teach us very much because the machine has just learned to guess the same answer every single time. So in determining how to define this aspect of functional recovery, we assessed each of our end study metrics for their distribution across histograms of different bin numbers. You can see 2 of which are pictured here. And ultimately, we chose probe for memory retention because of its relevance to a commonly tested aspect of recovery, being that memory retention, its widespread use and broad application throughout the TBI literature as a measure of cognitive performance, and its more even, although you can see it's not perfect, distribution across 2 histogram bins. Now this allows us to create a binary classifier if we call the left bin not recovered and the right bin recovered, while being empirically supported by the fact that we didn't set any kind of arbitrary boundary between the data points. So now we need to decide which supervised learning classifiers we want to train on our data set. Now, the answer to this is not one or the other, it's going to be multiple. And here's why. So imagine if you or I were assigned a task and told what the goal was, say, drive to campus from my house right here. We could come up with very different strategies that achieve the same exact goal. And this is true for these classifiers as well. So they all learn to classify their subjects, but they do this in different ways. The ones I have listed here are the ones that we chose to test because they are commonly found throughout both the computer science and biomedical literatures. So I'll briefly run through the strategies each of these models used to kind of give you an idea of what's going on behind the scenes. So we may have heard of decision trees as they seem to be popping up more and more in recent times. So when we're talking about decision trees, you can imagine a flowchart where these separation points are formed and determined by what's called information gain. So that is, during training, the model assesses which breakpoint leads to the biggest separation of groups. That is, if you had 10 samples, breaking that into 5 and 5 would have a greater information gain than breaking it into, say, 9 and 1. However, you can start to see how this can become overfitted because these models can separate out each subject one by one by one by one, and that's not super generalizable to new samples in a setting where we ultimately want to be making predictions. So then a random forest pictured here on the right is simply a bunch of these decision trees, except the final outcome that you get is going to be the majority vote of all of these different trees. Moving forward, Knearest Neighbor is what's called a lazy learner, and that it simply memorizes the training data that you give it and then waits for the test questions instead of creating a model to handle those future instances like that decision tree did with the information gain breaks. And so, you can imagine something like a take-home test where, we'll get the questions, you could go on your computer, press Control Find to look for relevant keywords. Not that any students would ever do this. But that's what Knearest Neighbor does. So when it sees the first test sample, it would then compare to the nearest feature vectors. The majority class of those neighbors, the nearest feature vectors, then becomes the classification of the test sample. Moving forward into support vector machines, or SVMs, if you take a look at this graph I have pictured here on the right, you can see there are a number of lines, or quote unquote hypotheses, that would perfectly separate out these two different colors of dots. However, a support vector machine attempts to find that optimal decision boundary. That is, what line will clearly separate the classes from one another with an optimal boundary determined by support vectors. Now, these support vectors are the points that are closest to the edge of each class and thus are the most difficult points to classify. And this technique is widely seen in the biomedical literature, so some people may have seen it once or twice before. Moving forward, if we all get a little bit nostalgic and think back to our college statistics class, you might recognize that theory of probability there on the top. And now we've all had to address questions like, what is the probability a sample will do something, end up like this, given their x-axis and y-axis values? So where on that plot do they end up given these two metrics? Now, of course, these problems always make major assumptions that all attributes are independent, and this results in the criticism of the model being very simplified. However, despite this simplicity, the model has actually performed quite well. Lastly, if we take a look at what's called a multilayer perceptron, this is actually an artificial neural network. So artificial neural networks are a series of layers that begin with an input, work their way through nodes in what are called hidden layers. I have one pictured here, but you can have many. And then eventually reach the output layer. So this is reminiscent of the biological makeup of neural circuitry, or simple neural circuitry. But in a multi-layer perceptron specifically, we're typically looking at that artificial neural network where each node is interconnected. So every dot here is connected to the dots in the next layer. And then these models are trained by updating the weights between nodes, which are depicted as the lines or arrows you see in this picture. So, while clearly a great deal of time in machine learning studies is spent on this pre-processing, feature engineering, coding the eventual implementation of your research question, you eventually get to the point where you get to train and test your models. So there are a number of ways to assess performance and validate your findings. I won't go into great detail here for the sake of time, but briefly, we separate our data into folds and use the majority of our samples to train our models. These trained models were then tested on their ability to accurately classify subjects that were previously set aside before training. So, the models had never seen before. So this was repeated 10 times with different data folds, that is, different training versus testing samples, and then the mean accuracy will be reported. So as a brief reminder, our research question was, given metrics from the first 7 days post-injury, which you see here on the top listed as input, can a machine accurately predict performance on a memory retention task 1 month after injury, which you see pictured here on the bottom? Now, this graph on the right, there it is, depicts the mean accuracy of the machine learning classifiers that I just ran through. Of course, they are abbreviated here on the bottom. However, the machine learning classifiers tested relative to that dummy chance control. This would just be, flip a coin, is it this or this? And notably, the SVM, that one that looked for the optimal decision boundary between classifiers, performed with about 62% accuracy versus the 48% achieved by the control. While this is far from perfect and not quite where we want to be, it does suggest that there are patterns within the data set that are allowing some of these classifiers to accurately begin to identify the recovery class from the not recovered. Now, this being the case, we're establishing different ways that we can augment our data set because we think that the biggest limiting factors right now is that we really only have about 10 subjects per treatment group. So we foresee doing this using techniques that are pretty widespread in computer science that allow you to actually generate synthetic examples for training specifically. That is, we hypothesize that this will better highlight the underlying patterns while still being generalizable to new instances because testing will only ever be done with real examples that were collected in the laboratory. Furthermore, as a prerequisite to creating an integrated system that could accurately predict some of these optimal treatments, we need to ask the question of whether a machine could learn to classify treatment given input data from the entire first month of recovery. That is, if we look at the pairwise comparisons of two treatments and ask the machine to identify which treatment each subject received based on the multivariate analyses it conducted, then you can see that the machine is actually very, very good and nearly perfect in some cases in understanding which treatment each subject received. So this tells us a few things. One, that different treatments are creating very different recovery profiles. And this is extremely interesting because we can now take this a step further and integrate these systems as an informative component regarding which treatments are optimal for subgroups of the TBI population. Furthermore, these findings can help us identify which treatments might be best suited for combining as a therapeutic strategy by understanding which treatments led to functional recovery benefits via very different profiles. This also gets us one step closer to understanding some of the complexities that we see with dose-response interactions or with the different recovery profiles of each individual treatment. And lastly, although I didn't picture it here, when we ran the pairwise comparison of different doses of the same drug, the machine had a much, much harder time in classifying the subjects from one another. So still on the topic of classifying subjects by treatment, we then handed the machine all three of the therapies that I discussed on the previous slide. So you can see here we have EPO, minocycline, and Keppra. And we gave all three this time instead of pairwise, so instead of binary, two classes that it could guess from, it now has three. And the machine was still quite good at accomplishing this task. That is, quite good at taking any sample out of the bunch and saying it received EPO or it received minocycline based on how it performed across that month of pre-sacrificial metrics. So currently ongoing work is we're going to see whether or not we can scale these findings. That is, if we keep adding more and more treatments beyond these two or three, we expect we'd see a hit in accuracy, right? Because if you have 10 options instead of two, you have a much lower chance at getting it right. However, we've created an architecture that now allows us to have pairwise comparisons of every single possible pairwise combination in whatever, n number of treatments we've included, and then a master classifier that can use a confidence scheme, a probability or likelihood to give us one final output of we believe this is a treatment that particular subject received. And this will be a very important step to make these findings more reflective of the state of the clinical state where you typically have more than two or three possible therapies. So briefly, just to take home from all of these words about computational techniques, we found that machine learning does show promise in its ability to predict defined recovery. Although that is currently far from perfect at this point, it was still significantly better than chance. Furthermore, machine learning is especially good at identifying which treatment each subject received, suggesting that there are unique patterns that are underlying the treatment effects that we see in our patients or in our rats and our subjects. So moving forward, we have to assess the performance using different recovery metrics. So like I said, we focused on memory retention and probe, but we could change the output to, their overall performance in the water maze, maybe even something tissue related, or a combination of them to make this more reminiscent of the big picture we're trying to attack. Furthermore, we aim to integrate the systems that we have, identifying subgroups and identifying recovery profiles from our treatments in such a way that we'll be able to inform the identification of optimal therapies for the specific subgroups of animals. And then moving forward is just, the big proof of concept, since the overall point here is to bring these techniques into the laboratory arena. We want to apply these techniques and the overall workflow that we've established to another preclinical data set to say, hey, look, they are relevant, they are providing these novel insights, and more people should start considering them as ways of analyzing their laboratory data. So with that, of course, I'd like to acknowledge my mentors, Helen Bramlett and Dalton Dietrich, and our whole team. You can see pictured on the right here. Of course, this project is super interdisciplinary and would not have been possible without the help of those over in computer science and Dr. Lauren Shapiro in physical medicine and rehabilitation, and all of the insight we've gotten along the way from my committee members who have really, taught me a lot in how to effectively communicate across this intersection of computer science and neurotrauma, where the same words mean a lot of different things to people in different fields. So with that, if there are any questions, I don't know how to unmute people, so.
Hi, how are you? It's Juan Pablo here. Very good job. I just have a question about the accuracy in your EPO versus minocycline.
Mm-hmm.
The accuracy was quite high. Are you concerned with overfitting? When you have such high accuracy, it may be harder to predict future outcomes.
Yeah, I mean, different models are more or less prone to, let's see if I can go back, overfitting than others. Yeah, you can see that here. But I'm a little bit less concerned about it since you see in CART, which is going to be our decision tree, you have random forest here, which I think are the two I discussed in terms of overfitting, are both performing well, which gives me a degree of confidence that I'm not as concerned about overfitting. But if it were just one that we're doing, amazingly well, then yeah, that would be a concern.
Cool. And what was your split ratio for the train to test?
So I did a validated K-fold. So it was 10 folds of the entire data set. So you had 9 and 1, and then you repeated that with each fold for the testing and then reported the mean accuracy. So it would be a 10 to 1.
Cool. Thank you.
Oh, wait, I think I see Dr. Bramlett in the chat. All right, so how would you go about translating your preclinical findings to the clinic? So what we're really looking at here is establishing a useful workflow. That is, we can use translation, we can translate these to the clinic by identifying which methods were useful and then looking at the common data elements. That is, if we see in our data that physiology was very telling or biomarkers were very telling, then that gives us a leg up on the clinical data because we know what we need to search for rather than picking everything out and by brute force picking out the relevant features in the clinical data set where there is a lot more, and that would not really be possible by brute force. Furthermore, we can take the architecture that we develop, especially in something like these treatment comparisons, that allows us to scale up to more treatments and identify these different recovery profiles directly to the clinic if we have the same common data elements. And then furthermore, we actually do have a study in mind doing exactly that, taking these architecture, taking these common data elements to the clinic by working with the model systems group here at UM and nationally. And we have access to that data set. So maybe next year we'll get to see how well that actually works. Any further questions? Well, if no one has any further questions, then thank you all for coming. I hope it was relatively clear and informative. And if you have any questions you think of later, feel free to email me.